Hello, and welcome to the Data Engineering Podcast, the show about modern data management. Have you ever woken up to a crisis because a number on a dashboard is broken and no one knows why, or sent out frustrating Slack messages trying to find the right dataset, or tried to understand what a column name means? Our friends at Atlan started out as a data team themselves and faced all this collaboration chaos. They started building Atlan as an internal tool for themselves. Atlan is a collaborative workspace for data-driven teams, like GitHub for engineering or Figma for design teams. By acting as a virtual hub for data assets ranging from tables and dashboards to SQL snippets and code, Atlan enables teams to create a single source of truth for all of their data assets, and collaborate across the modern data stack through deep integrations with tools like Snowflake, Slack, Looker, and more. Go to dataengineeringpodcast.com/Atlan today, that's ATLAN, and sign up for a free trial. If you're a Data Engineering Podcast listener, you get credits worth $3,000 on an annual subscription. When you're ready to build your next pipeline and want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows, or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode today, that's LINODE, and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host is Tobias Macey, and today I'm interviewing Matt Forrest about doing spatial analysis in SQL. So, Matt, can you start by introducing yourself?
Yeah, hey, my name is Matt Forrest. I head up the solutions engineering team at Cardo. We're a geospatial platform that focuses on spatial analysis, and a lot of our work overlaps with spatial SQL. So that's a big part of our day to day on a regular basis, which is a great topic for us to chat about.
And do you remember how you first got involved in the area of data management?
Yeah, I mean, I think anyone in geospatial has to work with large or complex data sets, right? Geospatial data comes in lots of different formats. There's hundreds of different individual file types that you have to work with. So by nature, I think anyone who works in GIS or geospatial has some familiarity with data management. There's a lot of tools from like a kind of a data engineering perspective. But what I found is the most efficient way is to bring all those data sources instead of managing them in different files or locations into a database. And the best databases for geospatial happen to be using spatial SQL. And I say spatial SQL, that can mean many different things. That could mean a data warehouse, something like a BigQuery or a Snowflake, and commonly that also means PostGIS, which is the geospatial extension of PostgreSQL. So that's how I got started working with it. I think a lot of people in GIS don't necessarily start with SQL first. They're working with maybe even desktop tools or notebooks that use libraries like GeoPandas, but still working with the core files. And then eventually, as things get complexer, you work across an organization or team. There's lots more management layers that you have to put on top of it. And Spatial SQL provides a really great way to actually do that. So, from a spatial perspective, you get all the benefits of everything that happens in the SQL world, plus some really efficient processes to do the analyses you were already doing, on a local or desktop level. So
one of my kind of most involved forays into doing work with spatial data was a combination of some Python scripting, QGIS, and generating some KML files to be able to generate a PDF of a heat map of network links between different IoT devices on street hardware in San Francisco. And that was a very convoluted and painful process. So I definitely kind of am sorry that I missed out on the kind of revolution of tools that are available over the past decade.
Well, that sounds very familiar, and that welcome to our world. So.
Yeah. And so I guess before we get too much into the spatial SQL side of things, one of the things you said was that you're working at Cardo where you do a lot of work with spatial analysis. And I'm wondering if you could just talk to some of the types of use cases that is applied to and some of the kinds of analysis that you might be doing on these spatial data sets.
A lot of geospatial work tends to go back to the interaction of spatial data. So you're looking at a few different components, but it's the spatial relationships between different features, like which things might touch or border another feature, What's the influence of those features? What are the influence of things within a certain distance? So you start to see and layer these spatial relationships onto each other. How much does one thing overlap with another? So on and so forth. Now, how you use that and study that, you apply different statistical methods to that. Of course, there's also a time series component to that as well, how things change over time within those spatial relationships, right? Do things move or change or progress as you look at that from a spatial temporal perspective. That's the pure spatial data science, right? Is using spatial relationships along with statistical methods to understand, phenomena in the real world, right? I would say on top of that, we also use, spatial features and machine learning workflows. So for more of a general data science community, we would call that, where you call that feature engineering, we call that spatial feature engineering. So it's taking those same methods to say, okay, if you're studying housing prices, right? What's the median income of the census tract that this house falls within? Or better yet, what's the median income of the census tract plus the surrounding census tracts that house falls within? And that's a very simple example, but you can extrapolate that out over lots and lots of features, and then you start to whittle those down to the things that actually have influence over a housing price. So that spatial feature engineering, I think, is one area that we I think can be used by other data scientists that maybe aren't using geospatial on a day-to-day, but one that's really interesting as well. Now, how we do that at Carto, we do a lot of workflows in Python. Certainly, a lot of these libraries are surfaced that way. But more and more, what we're seeing is that we can actually bring these workflows into some of the data warehouses or databases through user-defined functions. So actually bringing those in and either creating Python scripts on the database or even just using core SQL to add these statistical methods and then scale that up on quite a larger level just because of the computing power that data warehouses provide you. You can store a ton of data. You don't have to move the data around. You can do it all on that level, and you can use a common language to do that, which is SQL in this case.
And so, in terms of the spatial elements of the SQL dialects, you mentioned PostGIS, which is probably the most well-known implementation of that. I know that there are other sort of plugins for things like MySQL and other database engines. And I'm curious if you can just talk to some of the types of functionality that are needed to be able to support these spatial analysis in SQL dialects, and if there has been any kind of emergent standard that ties together these different database engine implementations.
Most people are starting to follow the lead of PostGIS, and I would say that across all the different databases or the different implementations. So I'll start with from a non-data warehouse level. Because most of the data warehouses have followed like the sort of function structure of PostGIS for the most part. There's other spatial databases out there. There's, like you said, implementations for MySQL. There's Spatial Light, which is a implementation for SQLite, and PostGIS being sort of the most well known and I think fully featured. So there's a ton of development that's gone into that project. Most spatial functions, well above 90%, are going to start with ST, which is shorthand for spatial type. Right. And so it's ST underscore, and then you can see the different functions. So if you ever see a function that looks like that, it's probably dealing with geospatial data. And there's lots of functions, right? You can, manipulate geospatial data. You can turn text into a geometry. There's simplification of geometries, measurements, and what's the perimeter of a polygon, creating geometries. So there's a wealth of stuff that can be, really useful, and some of those utilities that help you do and transform these things. But there's also, like I said, if you go to that spatial feature engineering, those spatial relationships, things like intersections or overlaps or what falls within another polygon, measuring of distances, finding the count of things that fall within. And then there's even some window functions like, creating clusters. There's an implementation for a spatial DB scan that is, is used, I think, PostGIS, and also BigQuery have implementations for that. So you're seeing all of those different types. So I would say for the most part, that standard of what PostGIS has set forward of what is ST intersects carries across most of the different databases or data warehouses. So you can find that, like that function, for example, is pretty well used, and you can find it across BigQuery and Redshift and Snowflake. And we're working on implementation for Databricks at Carto. There's a project called GeoMesa that implements that in like a Spark ecosystem as well. So there's lots of usually if you see one, it's probably similar with slight nuances potentially across all those different implementations. So,
and as far as the actual implementations themselves, given that they might share a function signature, I'm curious what you have found to be the level of consistency in implementation and accuracy and some of the ways that you might validate that, or some of the edge cases and gotchas that you've experienced where maybe there's the same function name between PostGIS and BigQuery, but there's maybe a difference in terms of the default level of accuracy as far as, how many decimal places to go out when you're trying to do some aggregate level roll up or anything like that. And then to your point of creating these user defined functions, also being able to hew to the same function signature and underlying implementation.
Yeah, some of them deal with data, and some of them will deal with the function implementation. So from a data side, if we think of two state borders, right, and you have a shape file or a GeoJSON, you put it in your spatial database, you would assume, looking at them on the map, that the border follows the exact same. A point on one side of the border is the same on the other, and even a slight variance of that, if the point slightly overlaps and you're using different functions, could throw off the different functions. There's some really great resources that explain the difference between ST intersects versus within versus overlaps. There's a lot of these functions that have just slight variance between them, within the individual implementations. And then with between the different database types, there's different tolerances between these things, right? So I don't know the exact numbers or the tolerance thresholds for BigQuery versus PostGIS versus Snowflake, but it should be in all the documentations. But for example, ST intersects, there's a slight tolerance of overlap, right? Very, very small, that will say, even if it just slightly overlaps or was within this distance, it will consider it true as an intersection. So it will catch some of those edge cases. So you might run ST intersects for a specific state, and you might get the bordering states because maybe they just are falling within that slight variance, and that might look different between the different implementations. So I always encourage everyone to get very good at reading the docs. All these services are very well documented. We'll go into detail on that, and then understand the differences between the function types. And some of them are not always, you have to read them and understand what you're using and how to kind of use them in bulk and these different things. So there's lots of ways to use them, use the docs, and kind of use them carefully. There's some great resources out there. I'll send some. I definitely recommend, if you want to get very deep into this, Paul Ramsey, who's a major contributor to PostGIS, he has a great blog that talks about it as the releases for PostGIS come out, some of the different things they've done to improve the speed of ST intersects. There was a previous workflow that they used to kind of subdivide geometries and, make the intersections faster, then regroup them. And they've actually implemented that in the core function. So, you can kind of follow the development of these tools as they go along, and even at a function level, what you can do. So there's lots of great blogs and resources out to actually check this stuff out. So,
and going back to your point of outside of the database environment, when you're working with geospatial data, you might have 100 or more different file formats and data types to represent different utilities, or sometimes it's the same information, but for different use cases where perhaps you're working with a raster file versus a vector file. And so I'm wondering if you can just talk to some of the work that's involved in understanding what is a useful common representation for all of these information sources and information types, and being able to translate that into a useful representation to store in the database so that you can scale these analyses across multiple different data sets, and just some of the data engineering and transformation work that goes into having this kind of common representation of the information that you're trying to analyze.
yeah, I think I've seen a sort of I wouldn't say a boom, but a growing trend in more and more people starting to either call themselves or post jobs for geospatial data engineers. I think it's become a unique challenge. Like I said, there's hundreds of different data types. There's common ones that you'll have, shape files, you'll have GeoJSON, of course CSVs. Getting a little bit deeper, you mentioned KMLs and KMZs, but there's so many different types, right? And even weird ones. There's ones I've never heard of or used. There's the Norwegian SOSI standard vector data set. there's Oracle spatial data types. There's so many different. You could go on and on, right? So I'll spare everyone the list here, but GDAL, the Geographic Data Abstraction Library, is the best resource. I would recommend everyone sort of check that out and use it. And it's an open source toolkit. You can install it locally on your machine. There's Python drivers as well as many other drivers to actually use that. And it's built to transform spatial data types, either raster to raster, vector to vector, or you can actually go from raster to vector or vector to raster. There's tools for creating and manipulating geometries and handling projections, which is a whole other component of this. So, just the challenge of taking all that data and getting it into the right formats or projections or common cases there is a difficult one. And how do you scale that too, right? When you're talking about planetary scale imagery, right? You're talking about, pixels that could represent 3 meters or 1 meter on the globe, and you're talking about it at a massive scale that's hundreds of millions or billions or even trillions of individual sort of records, right? So there's a whole cloud architecture behind this as well in terms of bringing that data into a database, right? So there's a huge effort to do that, but PostGIS has amazing tools to do this for both raster and vector data. They have GDAL drivers that you can leverage through some of their command line tools in these different places. From a cloud perspective, there's some really interesting stuff we've been doing with Google Cloud and their data flow product, which has Apache Beam installed. There's a library that we've worked with called GeoBeam, developed by Travis Webb at Google, and that actually brings some of that GDAL functionality as a file, a file-based source for geospatial data to scale that, in a serverless setting. So once it's there, of course, you've addressed all these problems, then you have some of these common ways to query and intersect and interact with this data to draw some insights. But there's huge challenges just on that front end of getting the data in the right spot.
And then in terms of the kind of data modeling that goes into once you have transformed this into a common representation, whether that is GeoJSON or KML or whatever it is that you decide is most effective for your use cases, what are some of the considerations that go into how to think about segmenting these data sets so that you can join across them, so that you can build your analyses, and just some of the kind of data modeling concepts that are necessary for working with these geographic representations and how that might differ from purely tabular data sources?
Yeah. So we've faced this challenge when we built our data observatory at Carto, which is sort of a data marketplace of sorts. We have challenges from the scale of data, number of records, to the complexity of geometries. There's very detailed or granular geometries. Those geometries change. The Census Bureau might update the census block polygons every year or so. So there's all of that changing data. There's a few things I would recommend. Number one is segmenting your geometries versus the tabular data associated with them and being able to perform effective joins. I saw a post a while ago on how Airbnb sort of segments their data, and they expect a lot of their team to be able to join or aggregate. That's sort of the same process we have in our data observatory. So our geometries are separate from the tabular data associated with them, and we join them on a common geo ID, whether that be a unique identifier, maybe something like a block group or census tract ID. And then we have a table schema to sort of how we name our tables, right? Effectively, you can say, here's the country it falls within, here's the geometry it's associated with, here's the, time span of that data, and then how can you create those joins effectively, and then pull that data set with the geometry plus the tabular data associated with that. The second reason for that is if just a storage perspective, if you have a really complex geometry, those geometry records or rows can get quite large. So if you only need to store them once, and then you can do the aggregation, and then the last step, just join to that geometry file. So that's like the biggest recommendation I would have. There's certainly steps you can do to simplify geometries, but you could lose relationships or different pieces with that. You're sort of sacrificing as you go along. But that's how I would that's my number one recommendation, is being able to have and leverage the power of SQL, which is saying you have those joins and those different pieces, and then from taking them out of the database, right? If you need to put them into common file types, there's lots of great tools for bringing that data back down to a shapefile or a GeoJSON or things like. So I think that's kind of how I would set up the infrastructure. So.
And so for people who are starting to work with these geospatial data formats and they want to be able to start to build up these analyses, how much background knowledge is necessary as far as some of the principles that go into being able to understand the features that exist in these geographic representations, some of the complexities that exist because of the fact that the Earth isn't a perfect sphere, being able to understand what the mapping scales are between the different representations, being able to translate between different units where maybe the geometry in one table is represented in square meters, in another case it's square miles, and just being able to make sure that you are building your analyses accurately and any sort of common tooling that exists in these SQL extensions that allow you to encapsulate more of that knowledge without necessarily having to have a geospatial expert doing everything.
Yeah, there's a few ground rules. First is understanding the projection of your data. Now, projection is the flat representation of geographic data from the Earth's surface, right? So anytime you project data, you're making a sacrifice in terms of, accuracy and measurement of distance. You could be, it could be the visual representation of the data, understanding, what that projection is and some of what it might potentially sacrifice is important. Now, for most spatial analysis, you want to preserve the relationships, right? The distance, the measurements, and things like that. So that's important. That's why, that's sort of a common projection. Most spatial databases, if they don't have a projection or only have one, use WGS 84, which is the ESPG code. If you look in the SQL, is 4326. So that preserves some of those relationships that are, you want to be able to measure and interact with. There's basically two spatial data types, if you think of that from a SQL perspective. So the first one is a geometry, right, which is when your data lives in a projected coordinate system or the flat representation of the Earth. The other one is a geography, where your data is represented as spherical coordinates on the Earth. You can even create spherical coordinates in other places, but that's the very high level between those two representations, right? So, in terms of measurement, right, there's certain things where you're measuring on the flat Earth versus the curvature of the Earth. If you were to have a geometry versus a geography in PostGIS, you might see slight differences there. So just those are things to be aware of, right? The curve of the Earth is going to have some impact there, and specifically if you're doing really detailed analysis, like a line of sight analysis, right? You want to understand things like, of course, elevation and blockages of a line of sight, but also eventually, the curvature of the Earth is going to play an impact into what you're doing. It's important to kind of, understand the differences there. So those are some ground rules. Understand your projection, understand what, spatial data type, geometry versus geography you're using, and understand, the use case and how accurate those measurements need to be. For a lot of things, if you're doing that on like a local or a city level, the differences will be fairly minute, right? They're sort of slight, but if you're going on like a national level or on a global scale or even a statewide scale, you're going to see those slight differences, and just being aware of that when you're using the spatial data is pretty important.
And as far as the details of the projections, as you were saying, if you're working at maybe the town level, you don't have to worry about that too much. I'm curious, what are the best practices of saying, if you're at this particular level of scale, you can mostly ignore that? And then what are the gradations as you go up from there to saying, okay, now you absolutely have to make a very informed choice about which projection you're going to use because of the type of analysis you're trying to do, and maybe some of the ways to map between the format of the aggregation or the statistical methods that you're applying to these geographies or geometries and the projection that is necessary to be able to support that, and determining sort of what the level of accuracy is across those kind of matrix of choices.
I think these are my ground rules. So they're specific to my domain expertise and the things that I work on. So I'll caveat them with that. If I'm looking at something at maybe like a metro area level, like like let's say the greater Dallas area or something like that, that generally, you're going to notice a minute difference between things like distances or things like that. There's a subset of use cases, like I said, that will be important for even on a very local or small scale. And I'm talking about distances of miles. very short distances can have some impact. When you start to get to maybe a more statewide or national level, that's when you want to be conscious of the projection that you're using and the analysis you want to or the things you want to preserve. So if you're visualizing data, you want to preserve sort of the visual representation or spatial layout, right? And there's different projections that you can use for those. There's different projections you can use for spatial relationships to preserve distance or the actual distance or relationships between those features. At that point, you can start to study that and pick consciously which ones you want to use, especially if you're measuring distances, and understanding that there's if I'm measuring between like LA and Dallas, right, there's going to be a difference if I use a geometry versus a geography, and that there's it's going to that curvature of the earth is going to make an impact in terms of how long that is. Those things are important, and you want to keep that in mind. And also, if you're looking at things like elevation, if you're getting into like 3D data, maybe there's a z coordinate involved. Like now you're starting to there's even more layers you start to add in here too. So
as far as the kind of statistical methods, we were discussing some of the expertise that's necessary from the geospatial standpoint to be able to manipulate this data. But then from the statistical analysis side, what are some of the backgrounds that are useful to be able to understand what statistical methods or what kind of mathematical approaches are going to yield the best results for these types of data sets, and maybe some of the ways that the geographic nature of the information, and maybe you're joining it with demographic data to be able to do some type of census analysis based on neighborhoods within a city region or something like that, just how you're able to kind of span those different knowledge domains.
yeah, I posted something on LinkedIn, I think last week, kind of looking at the geospatial roles that exist in terms of job function and things like that. And I think they're starting to segment a little bit. If you think of it, I've seen some posts in terms of how data science has started to segment between a pure data scientist versus a data engineer versus an analyst versus maybe a machine learning ops person, and all these different roles, right? I would say the same is only starting in geospatial, and different roles have different domain expertise areas, right? A geospatial analyst they need to understand geospatial data, spatial relationships, and how they interact, and basically how to do some basic joins and interaction with data. So I think that's one level. They're not so deep into the statistical methods there, but maybe using some of the basics. For someone in spatial data science, having that statistical background and being able to join that with the spatial domain knowledge is really important. I think there's some different tools out there that make it easier for lots of other folks who maybe haven't explored that space. PySal is one of the most complete pure spatial data science libraries that I would recommend. It's the Python Spatial Analysis Library, and they have great analytical tools for using some really detailed methods and analysis types. So I definitely recommend checking that out for use cases like network analysis or location allocation, inequity and distribution, lots of different core use cases. And then on the data engineering side, it's understanding data types or relationships and geometry creation and things like that. So I would say depending on where you come into the picture in your background, right? If you have more of that statistical background, that spatial data science piece is probably where you would land. More of the analytical background, understanding spatial relationships, is that kind of you would map to like a GIS analyst. And then if you're more traditional like data problems or data engineering, geospatial data engineer has some of those core functions too. But I think there's an interesting kind of connectivity between that pure data science world and the geospatial data science world, and it's all sort of underpinned with the understanding and use of spatial relationships together. So,
and as far as the workflow where you have a new data set, you're trying to explore some of the interesting geographic or kind of map features of a new area, and you want to understand what are some of the types of questions that I can answer with this data, going from this exploratory approach to saying, okay, now I want to scale this and make it repeatable. I'm wondering what you see as kind of the tipping point between this makes sense to do on my laptop using PySal or GeoPandas, and then going to saying, okay, it makes more sense for me to load this into my database, do this all in SQL, maybe execute this as part of a pipeline so that I can do some of this geographic feature engineering that you were referring to earlier, and turning it more into this kind of repeatable flow that the data engineer is likely going to be responsible for.
Yeah, there's a few areas of, local, or, even a data science workflow, whether that's cloud or local. And I'll say it like that with, Python libraries and files that exist in a, file storage system. It works great, for doing some, one-off or, analysis where you want to study one phenomenon with one set of data, right? Let's say you want to start to scale that for multiple geographies or cities or something like that, and sort of use some of that on a repeatable basis. That's when I would start to look at a database, because you can, keep that data there. You can benefit from, fresh or updated data that's going into that database, and you're simply saying, you might be able to just interchange a table name and then run everything again and get a new result, right? Instead of, you still could do that with your files, but you're still on the hook for finding the right file and keeping in the right location and having someone update that. And there's an interesting quote that, geospatial has moved more and more towards the cloud, instead of, previously where it was, sits on someone's machine or on a USB drive, and people are passing those file types back and forth. So I think more and more when you start to say, okay, if I need to run this thing for multiple geographies or multiple times, or if I have regularly updating data, that's when I would start to look at that from a SQL perspective. And I think also in terms of this, if you're, if you're doing really large scale spatial joins, right? If I want to do a spatial intersection and underneath with points that are, numbering in the millions or billions, right? Then a spatial data warehouse makes a lot of sense. And even PostGIS can scale to reach some of these, capacities too. So it's really well engineered where you can do and use, some of those large scale spatial intersections. But when you need to, reach some of that really, high scalability, that's where that really comes in handy. And you can scale up, to trillions of records, or, like that enterprise level data that you might want to be using that has some location attribute behind it, that's, you may want to use with your polygons and do spatial intersections that way. So there's no one clear lever. I would say if it's something needs to be highly repeatable, if data is streaming in on, or changing on a regular basis, I think that's another key tipping point, and then scale, right? If you're, in terms of complexity of data, in terms of number of data sets, in terms of, the number of rows, all those things tend to lend themselves to more of a, a database first approach, if you think of it that way.
And as far as the kind of time dimension of working with these geographic data sets, where maybe you're dealing with satellite imagery, and so you're loading in new raster files every 24 hours for a particular geographic location, I'm wondering how you're able to start to incorporate some of these data quality considerations into that workflow, to be able to say, okay, this new piece of information for this geographical region is within this area of tolerance for, difference, where maybe the kind of geography of the snapshot for a particular expected timestamp is off by a meter because of variance in orbital velocities or something like that, and being able to say, okay, this is still within the range of tolerance for this geographical boundary that I'm trying to represent with this raster image, and then saying, okay, well, no, this other one, because there's been too much orbital decay, it's no longer close enough to the same geography. It's actually, 50 meters due west. And so now I need to say, I'm not going to accept that in this data import or for this particular analysis. Some of those additional complexities that arise as you're dealing with evolving representations of the same geographies.
Yeah, I think from my perspective, one thing that a lot of the imagery providers have gotten a lot better at is actually handling some of that on their own, and that's where I'm seeing a huge rise in that, like, geospatial data engineer kind of career path, right? Is actually handling those types of problems. So, a lot of the data that makes it to the end consumer has some of those considerations built into it. Of course, there's data checks that you would want to implement and bring in on your own, right? I think there's a few different ways to do that, but I think that pipeline sort of driven approach is the one that makes a lot of sense. You can actually check geometries as they stream through, or they batch through. If you think of it from that perspective, even GDAL can use some of that. So there's actually, spatial light is you can actually run SQL within your GDAL workflow and do some, intersections or checks that way. So how do you sort of check and understand is what's the tolerance, or is this same feature intersecting with the same feature from a few days ago or anything like that. So there's some quality checks you can build into your data pipelines, which is, from a geospatial perspective, we're generally thinking about, bits and pieces of these things, but we're also, there's whole other worlds we have to understand, from either data engineering or database management up until, complex SQL queries. There's all these other revolving areas, and I think that's why specialization is really important here, is that, can we build geospatial data engineers and have a robust background in everything around data engineering, but have that focus area as well to start to look at, some of these very specific problems that data engineers have worked on for a long time, right? To answer the question, it's twofold. I think one, it's an evolving space, and I think, well, some of the providers are doing a really good job at that already, but they're doing so because they're bringing in data engineers and helping them become geospatial. But I think also we're starting to see more people in geospatial start to gravitate towards those pieces as well, because they have that geospatial expertise. And the things that are enabling that are the common languages and tools to help communicate between the two, whether that be SQL or Python or command line workflows that people can share back and forth, right? These aren't locked away, in the ways that they were in the past. So that makes that interoperability really, really key as this starts to scale. But pipelines and, geospatial data engineering, I think, are really important pieces that are going to evolve as the space grows. So.
StreamSets DataOps platform is the world's first single platform for building smart data pipelines across hybrid and multi-cloud architectures. Build, run, monitor, and manage data pipelines confidently with an end-to-end data integration platform that's built for constant change. Amp up your productivity with an easy-to-navigate interface and hundreds of pre-built connectors, and get pipelines into new hires up and running quickly with powerful, reusable components that work across batch and streaming. Once you're up and running, your smart data pipelines are resilient to data drift, those ongoing and unexpected changes in schema, semantics, and infrastructure. Finally, one single pane of glass for operating and monitoring all of your data pipelines, the full transparency and control you desire for your data operations. Get started building pipelines in minutes for free at dataengineeringpodcast.com/streamsets. The first 10 listeners that subscribe to StreamSets Professional tier will receive 2 months free after their first month. And then going back to the level of support that exists in some of these different database engines that folks might be working with, I know that PostGIS is kind of the de facto best practice. If you're working with geographic data in a database, you should use this one. Obviously, some people are constrained where they can't just swap in Postgres because they decide to add a new data type, but I'm wondering what you have seen as the kind of availability of these geographic analysis capabilities in the SQL dialect across different database engines, and any evolutions of that support or interesting kind of up and coming projects that exist in this space.
Yeah, I think more and more we're getting parity, and more of the data warehouses are starting to push some of those features, and they're starting to adopt more of a pure spatial SQL dialect. So like GeoMace is a really interesting project. It adds SQL, spatial SQL type functionality to Spark, and allows you to have that same sort of language. If I want ST, as text, or some of those common functions, you can actually use and implement those in a Spark environment. So there's some really interesting. I think it's becoming commonplace. Like everyone in Geo's kind of understood and accepted that. Of course, there's some work that there's like the open geospatial community is doing to sort of create common spatial file types, whether that's for some of the Spark file types or things like that, to actually from a file format perspective, that work's happening as well. But I would say more and more of those features are trying to get that level of parity with PostGIS in terms of some of the functions that are there. In terms of advancements and interesting projects, at Carto, what we're doing is actually building what we're calling our analytics toolboxes, which is a set of functions that port net new functionality into databases or data warehouses. So if anyone's familiar with Uber's H3 spatial indexing method, that's one that we're actually using and bringing that in to actually create an H3, hex index on an individual point or polygon. You can create polyfills. You can, create H3 geometries and do spatial aggregations with those. And we're adding routing functionality. Of course, PG routing has existed for PostGIS for a long time, but we're adding, routing functionality, and then, more advanced pieces into some of the spatial, data science functions or functionality that you would see in PySal, bringing some of those into a spatial SQL environment, I think is really interesting. It solves some of the ability to not have to move a ton of data back and forth, and you can do it all at the database level, and even things up to creating tile sets. In PostGIS, there's functions called STS, MVT, that's a specific tile format for rendering vector data in tiles, which are really efficient ways to render map data online or in spatial applications. And then we actually tried to, we ported some of that functionality over to BigQuery. You can create tile sets and store them directly in BigQuery. So there's a lot of these extra use cases that are kind of finding more things and more geospatial workflows that you might be doing in other places and bring them into the database level to make that your sort of center point for doing spatial, everything from the data engineering to the spatial relationship analysis to spatial data science workflows, and then even into the actual visualization engines as well. So,
and in the actual storage layer, I'm curious what you have seen as some of the performance considerations as to saying, okay, well, I need to convert this vector file into a GeoJSON array or something because it'll work better in BigQuery because they don't have native support in the actual engine code to handle this file type as far as how it maps to their storage format or anything like that, and just some of the kind of low level considerations that go into maybe performance engineering around your analytical workflows to influence the way that you approach the actual kind of data engineering and data processing to be able to support these use cases.
yeah, geometry data comes in many formats, and there's a lot of like geometry assessor functions if you look in the different databases. So there's a lot of tools to create geometries from different data. That could be well-known text, that could be bytes, that could be other representations of that data. You could have numeric lat longs that you turn into geometries. So this is a long list of first of all, taking even GeoJSON data and turning it into a geometry in a spatial database. On the flip side of that, there's a lot of tools to translate that same data back out to different formats. Whether, like I said, that could be spitting it out as a GeoJSON geometry, or rendering it as a tile set type, or bytes, or these different, methods. I think understanding that how your data is coming in, first of all, if that's, stored as well-known text, that's certainly one way, or GeoJSON. Those are probably some of the more common ones. If you're having like a true geospatial file, maybe like a shape file, you're going to have some sort of geometry object or things like that. Understanding if you do need to translate that, from BigQuery right now, if you do that natively with their command line tools, the best recommended approach is to turn your geometry into GeoJSON, which can be accomplished once again through SQL, through GDAL, when you're turning it into a CSV that you can push up there. We use that data flow plus GeoBeam workflow. You don't have to account for that as much. It just sort of handles everything from the geometry creation, validation. If it's a raster file, it vectorizes it, reprojects it, does make sure it's valid as needs to be, and does all those different things. So like I said, there's for someone who's had these, I kind of have my foot in a little bit of everything in terms of the geospatial space. This data engineering piece is very interesting for me because of the scalability of and the massive amounts of data. Plus you can orchestrate all these things really nicely. So all these problems that you might have had before that you would do at a one-off place, I can just write them into a nice file for Apache Beam, set it up, deploy the container, and then I'm ready to use that again and again and again, right? So, but I think, generally, you're, understanding that you're going to get geospatial data in different formats. GeoJSON, a shapefile or geometry that comes from with a shapefile is pretty common, or well-known text. How you use that, you might have to validate those geometries. There might be points that are missing, right? You might need to connect polygon lines. I've seen that happen quite a bit before. And then there's even, things like geo packages that, might have multiple different geospatial files within them. So understanding the data that you're looking at is pretty important. Understanding, specifically if you're in a data warehouse, or some of the different methods that you need to get them in for like PostGIS. There's lots of tools to do that. But find the workflow that works consistently for your data, kind of leverage that. I definitely recommend checking out GDAL. There's lots of, it's sort of it's the Swiss Army knife. It has a little bit of everything and covers pretty much every single file type you might ever want to work with. And then you can set up some of those, workflows to bring that data in, and even, like I said, midstream, use SQL to do some of those transformations with Spatial Light and things like that. I'll send over some resources because each tool has its own ingestion process. There's BigQuery has command line tools, or you can use Dataflow. There's multiple different tool types for PostGIS. You can even load data by connecting your PostGIS database to QGIS, and then QGIS has GDAL through a desktop GUI if you want to use it that way. There's the copy methods are pretty common, for copying the CSV data and streaming that in. So there's lots of different ways to do so. But it's always, kind of understanding, okay, I have a geometry in this format. How would I turn into an actual geometry or geography on the database? And there's lots of functions to do that.
And so, in your experience of working with geographic data in this SQL environment, I'm curious, what are some of the most interesting or innovative or unexpected ways that you've seen those capabilities employed?
Yeah, I think in terms of innovative workflows, there were a lot of great talks at, I think it was PostGS Day 2021, just at the end of last year. People that are, loading spatial data into a database that, might have complex formats or coming from a variety of different sources. They're analyzing or creating, interesting insights from the data all in the database, and then rendering tiles to a web app. All that entire workflow up until the point where the tiles actually show up in a web app is all in a database. And there's of course there's an API layer that can serve the tiles, but all of that's happening there, all through SQL, which is pretty cool when you think about it, because even before you would the database could serve as the analytical layer. You might have to pull that out and as a data file and create tiles from that separately, and then the data load or ingest, some of that transformation might even have to happen prior. So you've kind of compressed three pretty complex workflows into one space or location, right? And that's some of the tools we're trying to create from a data warehouse perspective, is bring that same level of functionality into a data warehouse, and use all the great things that exist in data warehouses with some of their machine learning workflows or some of their data connectivity, and that opens up a lot of interesting possibilities from the geospatial perspective. So those are the coolest use cases that I've seen. Some other ones that are really interesting is with like the raster data. Raster data or Earth observation has always been kind of a really unique and interesting field. And it almost in ways sometimes they feel separate in the geospatial world. If people are doing analysis on census data or retail analytics, they might not be touching raster data, versus others that are using pictometry or Earth observation or satellite imagery and creating derivative raster analysis from that. Those two don't always feel interconnected in some ways, but now I think they're just starting to, because of SQL, and PostGIS has a lot of great functionality for reading raster data and creating analysis, or smoothing raster data. So there's some tools there. And then from like the data ingest piece, that data flow plus GeoBeam workflow I was discussing with BigQuery is great, because we set it up with a few other tools where I can kind of put a raster file in cloud storage bucket. The entire workflow automates, and then eventually have a table in BigQuery, shortly thereafter. So that entire process is automated. Then I can do an intersection on raster data plus my other vector spatial data, all within one SQL query, which is really unique and interesting. So I can either, ingest the raw data with, the color bands associated with them, or, I can actually, take the derivative outputs of an analysis and pull that in there, which opens up a lot of unique use cases, studying maybe deforestation, or we've seen some people leverage, those types of workflows for, agriculture study and understanding where, things are being planted. Even consumer packaged good companies, they want to use that data, over time to see where they're sourcing materials from. And if, these are actually sustainable, farms or practices. Are they replanting? How often are they replanting? What are they doing to actually, preserve the environment around them? So there's all of those types of questions that are being asked too, which you can't do without a satellite image or something, or something derived from a satellite image. But of course you have that plus other vector data. And then how do you then make that easy to serve up and interesting is actually bringing that up into, an application, which, you have your tile layers and your visualization that can also be run from the warehouse or the database. So all those possibilities make life very easy in places where it was potentially complex before, plus cracking into a wealth of other enterprise data that might be in these locations. Those open a lot of really interesting possibilities. So
All right. And in your experience of working with spatial data in a SQL environment for your own work at Carto, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
challenging lessons, for me, I had, when I started to learn, everyone learns somewhere. And that's what I tell everyone, especially as someone coming from a traditional GIS background where things are more file based or kind of the workflow you discussed, right? You're using QGIS or maybe a different desktop tool. You're pulling in some different files and translating them and then pulling them maybe into a Python workflow. Everyone starts somewhere. And, I kind of had a nominal understanding of, a SQL query and just building upon those lessons and continuing to go deeper is really great. I mean, unexpectedly finding new things that are maybe on the Postgres side of the house, maybe not the spatial SQL is great. I love Postgres triggers. I think, especially for, data that's being inserted to a database, let's say I have a point I can drop in from an application or a form somewhere. I can detect that on the table. I can geocode that point. I can enrich it and see, what's the population or a polygon it falls within. I can extract a bunch of other spatial data and then do all of that without ever touching it. It's like those really bad infomercials. You set it and forget it, and it just kind of happens. I think that's one of like those little unexpected discoveries of things are really great. Plus, when new releases come out, the ability to speed up or make things much more rapid, like that's that ST intersects that changed. They added some new took a feature that had been you could kind of do already, with different functions, but actually put it in the core function. Now you're much faster in spatial intersections and things like that. So those are some of the unexpected pieces. But even as you go deeper, you can PG routing is really awesome. You can make your own custom routing engine using your own data, and really do some complex stuff with that. We've done some really advanced, logistics analysis with that, just because you have to create OD matrices for multiple depots and potentially hundreds of thousands of deliveries every single day, right? You can't do that via a API endpoint, right? There's too much data there. So all of those different pieces are really amazing. And then I think it's the day-to-day things where you discover something or you change something or you run a query just a little bit in a different way, and you go from something that might take minutes to seconds, or finding a new way to use a subquery, then that makes life a lot faster. It's those things that are just every day kind of validate why you put some time and energy into using that. So
And for people who are working with geodata and they're trying to decide what is the best workflow for them, what are the cases where putting it into a SQL database and using these SQL extensions might be the wrong choice, and maybe they're better suited using some of these desktop utilities or Python scripting or putting it into a Spark cluster or something like that?
I would say if you're doing a lot of select star statements, it's kind of like, okay, you have it in database and that's great. But if you're not leveraging the spatial relationship features, if you're doing spatial, just pulling the data down and then doing the spatial join in Python or in a desktop workflow, I would definitely recommend taking a step back and saying, can I do that on the database and will it be faster? I think that's one. The other piece is if you're just kind of doing a join to a lot of other enterprise sort of data, a spatial join is the unique join, the relationship between two geometries, right? If you just need to aggregate some data and then join it to something else, you may not need to do a SQL component. You could join it by ID or some other ways like that. So it's knowing when you have a true spatial relationship, then it makes sense to kind of go that route as well. So those are some areas I recommend. And obviously I listed, like the scale of data, these, sort of the volume of the data that's streaming in or changing, and then the complexity of that data all sort of lend themselves to those use cases. If you're kind of doing one-offs or want to move very quickly and agilely and can use the files, or, like I said, just kind of use a Spark cluster or something like that, those are great choices. It's when you start to need to scale up and go from there that I think those are some logical points to be watching out for when you're working with this data.
And as you continue to work with these SQL extensions in your work at Carto, I'm curious, what are some of the things you have planned for the near to medium term as far as spatial analytics support or additional capabilities that you want to push into these user-defined functions for these other data warehouse engines, or just other projects that you're excited to dig into?
Yeah, I'm excited to keep bringing a lot of the stuff that I could previously just did in Python into the database or the data warehouse. So things like everything you look at in PySal, kind of how can I do that in a data warehouse or a database. Location allocation is one of the coolest ones that I found, which is sort of logically given a network, maybe like a road network, and a sort of set of demand, sort of either individuals or people living there or customers. And I have some service that needs to serve them, whether that be, a polling place or a school or a fire department or something like, in New York City, we now have these, 15-minute delivery grocery services. Where should I, given a set of, let's say 30 places I need to decide from, which are the 10 best that can serve that based on, do I want to have complete coverage or things like that. There's a great library called SPOPT, SPOPT in PySal. It's a sub package of PySal that actually does and addresses some of this. You can do it all in Python now, but I can see hey, can we generate the network faster, or can we compute the OD matrices faster in SQL? And then the last mile of that, we can kind of compute with the location allocation functions, and actually tells you, okay, here's your most effective places, your coverage is 86%, and here's how you can effectively do that. Because those are really common questions we get all the time, and there's lots of data that could be driving those decisions, in terms of where people are moving to or from, or mobility data, which numbers in the millions of or billions of pings and things like that. So it gives you a lot of flexibility to do those different things. So,
are there any other aspects of the work that you're doing at Carto or applications of SQL extensions to this arena of geospatial analysis, or any of the related considerations that we didn't discuss yet that you'd like to cover before we close out the show?
I think I covered a lot of the core ones. I think there's such a boom, in interest in this data, primarily not just because of, more and more, I think people looking at geospatial or modern GIS workflows and just the data science sort of, growth over the last couple of years, but the problems where we're starting to see and solve, everything from how, access was studied, or, in COVID, at the beginning, who can access a healthcare facility, where's your nearest pharmacy, all the way through things like supply chain or equitable distribution of vaccines, all these, and even how people moved, during the pandemic. There's just been an upheaval in terms of the way things happen in this world, climate change probably being one of the biggest ones, that there is a fundamental need for geospatial data, and that data is only getting bigger and more complex. So we're finding that there's a push and a need for these new tools, these new analyses, and new ways to surface those insights, not just as a one-off, pull some data, create a dashboard, and then it lives on the web forever, but on a regular, daily or hourly basis. Once new data comes in, how can I show those insights? And Spatial SQL allows you, like I said, that complete workflow from the data engineering and ingestion and ETL to the storage and management and querying, to the spatial relationships, and then to the actual rendering of the visual outputs that can be pulled into an application or a dashboard that someone can use and see. That all kind of lives there now, and that's exciting. It's really exciting. So that's where I get really excited to see how can you take that to the next level. So,
all right. Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I think I'll talk about it from my lens, which, of course, is from the geo side. I think, in terms of data management, I think creating some easy ways for discovery and using other data sets alongside your data is sort of a big gap. And it's always a challenge we've tried to sort of use and sort of address at Carto. If I have a data set in a specific city, what other data exists around there? What data points can I use? How can I enrich that other data? And we've created some functions to start to address that, to create easy enrichment across multiple different data sets. So if I want to enrich with census data, or maybe a premium data set, or, spend data or road traffic, doing that in one single shot, has always been complicated. So first of all, you have to go get all that data, bring it into a single location, and then run that enrichment and do how many ever joins you need to do to get to that insight. And then we tried to make that easy and orchestratable behind the scenes with the data observatory, which serves as both a discovery method of data, a marketplace, as well as an enrichment function. So that's probably the biggest gap, and I think one that's sort of unexplored Spatial feature engineering is the other, but that's a whole other topic. So, yeah.
All right. Well, thank you very much for taking the time today to join me and share your experience of working with all of these geographic data sets and applications of SQL dialects to that. It's definitely a very interesting problem domain. And as you said, one that is expanding in terms of use and importance. So appreciate all of the time and energy that you and the folks at Cardo are putting into that. And I hope you enjoy the rest of your day.
Same here. Thanks for having me.
Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.